Have you ever written the same class or method twice, once for user, once for product, and thought, there has to be a better way? That's exactly why C# generics exist. In this video, I'll show you what generics are, why they save you time, and how to apply them in real-world projects. All right, let's start with the big question. What exactly are generics in C#? Put simply, generics let you write code once and use it with many different data types without losing type safety. Instead of writing one class for integers, another for strings, and another for your own person object, you write it once with a placeholder type, usually called t. Later, you decide what t should be when you use it. See the difference? With generics, we only write box once, and it can hold an int, a string, or even a custom person object. No duplication, no messy casting. Before C# generics, developers often used object to make reusable containers. This works, but now you must cast back to the real type. The compiler doesn't protect you here because everything looks like object. The error only shows up at runtime. With generics, the compiler immediately warns you. That's what we mean by type safety at compile time. Now that we know what generics are and why they exist, let's look at the core syntax you'll use in C#. We'll cover three key parts. 1. Generic classes. 2. Generic methods. 3. Constraints with where t. Don't worry, I'll keep it simple and show short examples. This is a generic class. Notice the t after box. T is just a placeholder for the type you'll use later. When you create an instance, you decide what t should be. So box int is a box of integers, and box string is a box of strings. One class, many possible types. Okay. Here's a generic method. The t appears right before the parameters. This swap method can swap two integers, two strings, or even two person objects, and the compiler enforces type safety. Here's our first example. I have two integers, x equals 5 and y equals 10. Before swapping, we print them out. X equals 5, y equals 10. Now I call swap ref x ref y. Notice that I don't need a special method just for integers. My generic method takes care of it. After swapping, the values flip. X is now 10, y is now 5. The same method worked without me writing duplicate code for integers. Now let's try the exact same method, but with strings. I start with first equals Alice and second equals Bob. When I call swap ref first, ref second, it still works, even though these are strings. After swapping, first is Bob and second is Alice. So the power of generics is that we write the logic once, and it works for multiple data types, whether it's integers, strings, or even more complex objects. And that's why generics are so powerful. They give us reusable, type-safe methods without duplicating code. Okay, sometimes you don't want t to be anything. You want to restrict what kinds of types are allowed. That's where constraints come in with the where keyword. This says t must be a reference type, like a class. You can't use int or struct here. Other common constraints are where t, struct only value types. Where t new must have a public parameterless constructor. Where t some base class must inherit from a specific class. Where t, like isome interface, must implement an interface. You can even combine them, Mempervro. Generic classes use t to make one class reusable for many types. Generic methods let you write algorithms once and add them to any type. Constraints give you guardrails, telling the compiler only these kinds of types are allowed. These three building blocks form the foundation of generics in C#. Next, let's put them into practice with a real-world example. In our blog API project, built with clean architecture, EF Core, and PostgreSQL, we've already set up some endpoints to insert, update, delete, and retrieve both posts and tags. Right now, for example, we can create new tags and fetch a tag by its ID. Everything works fine, and the new records are being saved correctly into the tag table in our database. As you can see, both repositories declare the same functions: get by id async, add async, update async, delete async. It works, but it's boilerplate. We don't want to repeat ourselves. So here's our solution: a generic interface ibase repository t. Notice the where t base entity constraint. This ensures that only entities like post or tag can use this repository. This way, we guarantee consistency across our data access layer. After that, we create base repository that implements ibase repository. This base repository T uses EF-Core's set method, so it can handle any entity, posts, tags, or anything else we add later. And because it's generic, we only write the CRUD logic once. We update iPost repository to extend iBase repository post, and iTag repository to extend iBase repository tag. Now, both post repository and tag repository are super clean. They just extend base repository and their own interface. No duplicate CRUD code, no boilerplate. If we need extra methods like get post by author ID, we can still add them here. But all the shared functionality lives in one place. So what did we achieve? We removed duplicate CRUD code. We made repositories consistent and easier to maintain. And we opened the door for reusability. Now any entity can plug into this system with almost no effort. All right, let's do a quick recap of what we covered today about generics in C#. 1. What generics are. Reusable code templates that work with many types. 2. Why they matter. They reduce duplication, give you compile time type safety, and keep your code clean. 3. Core syntax. Generic classes, generic methods, and constraints like where T class. 4. Practical examples. We built a repository T to avoid duplicate database code, and a result T wrapper for safer error handling. Thanks for watching, and see you in the next one.